Okay, this is where we stopped yesterday. So we defined, so what we're aiming, so our goal is we defined the primitive recursive functions. This was our first approximation to computability. So we're thinking maybe these are the computable functions, but then we constructed non-constructively. So we came up with a proof that there exists a function which is not primitive recursive. However, by diagonal argument, you construct this function and you kind of convince yourself that this is computable. So there is a function that is computable but not primitive recursive. So our next step was to expand primitive recursive functions. And so the first step towards expanding it is defining a bounded operator, bounded mu operator. And then we said, so what is a bounded mu operator? So you have a function that's with r inputs and one output. And what is, so you create a new function. And what does this function return? Well, it plugs in for the first variable. This is how it's defined here. So for the first variable, you plug in, you start at 0. So you plug in 0, 1, 2, 3, 4. And you check whether this equation is satisfied for each iteration. And once you find that this equation is satisfied, you return the iteration you found this on. So if, let's say, if f4x is 0, and f3x and f2x and f1x is non-zero, and if at step 4 you found it, you will return 4. And if you do not find your iteration, so if you do not find the solution all the way up to n, so it's like a for loop from 1 to n, and if you go all the way up to n, you just return 0. Right, so this function is always defined, so it either returns 0 or it returns m. It goes all the way up to n, and that's it. Right, and so this was we gave examples of this, not very good ones, but anyways, and so we do this, and the first proof that we have here, where we stopped, is that if your function was primitive recursive to begin with, your bounded operator is also primitive recursive. And here is this proof. So might as well write it here. So it's basically like induction. Proof is very induction-like. So I have to prove that this operator mu b f n x is primitive recursive. This is what I want to prove, right? So first I check it for 0. So I check that, well, mu b so mu b f0x, what is this, right? I look at what is this mu b f0x. So this thing can return two things. If you think about it, it can return two things. First of all, it starts checking, so it looks at the function like this, f(i)x, and it checks, is this thing 0, right? Where I goes from 0 to n, basically, if you want to do it for n. But in our case, n is 0. So I goes from 0 to 0. So what this will do, it will check this guy. Is f0x equal to 0? This is what this will do. If it's equal to 0, it will return the I, so 0. So the first case, it will return 0. If this function is equal to 0. If it's not equal to 0, it will end the loop and return 0. So in any case, this function returns 0 somehow. f0x is always 0. So this is a constant thing. So this is a primitive recursive. So this is just 0. So it's constant. So now let's look what m bounded f at n plus 1x is doing, right? So what is this thing doing? So first, it starts so let's write it out. So it looks at this. By the way, I didn't mention it last time, and there was a question. X here denotes many variables. So x can be x2, x3, x4, x5, x6. So it's like a vector. So this is just first variable, which is n. This is just natural number, and this may denote many variables, but it doesn't really matter. So it checks, is this 0? Then it goes f1x. If it's not 0, it's checks, so it goes f2x, checks, and then it goes to f, all the way to fn plus 1x, does this equal to 0? So if at some point it found 0, it stops and returns that. I cannot write it in a good way. So if f2x was 0, it will return 2. Here's the, so what this can now, what are the possibilities? The one possibility is that it actually the answer is yes to at some point. So let's say f2x is equal to 0, and then if the answer is yes, then this function will be equal to 2. But if f2x, so if before n plus 1 the thing was found, then the same exact thing will be found when I'm computing bounded operator of fnx. Because this thing is doing the same exact thing, but only going all up to fnx, right? So it's doing the same exact procedure, but it's only, the loop is going to n minus 1. Well, up to n. The loop here is going to n plus 1, the loop here is going to only up to n, and it will still find something here. So one possibility is that it is the same exact thing as bounded operator of fnx. So if the bounded operator at fnx was non-zero, that means the solution was found before n, then if you go to n plus 1, you're looking at the smallest solution, so it will also be found. So this is one possibility. This is the possibility when something was found here. Another possibility is that something was found here at the last stage. So maybe the answer here is yes and not this one. However, you found the solution here. Then your function will return n plus 1 because this is the step you found it. And it was not 0 all the way up to n plus 1 because it's the minimal solution. So it will return n plus 1. That means that fn plus 1 at x was 0, so the last stage was 0, and the solution was solution was not found before. So if the solution was not found before, you returned 0, but because you did not find the solution, not because it was done on the 0 step. So mu bfnx equals 0 means that solution was not found before. It was found at n plus 1 stage. The solution was not found before, and f0x is non-zero, meaning that you didn't get 0 because on the first step you got 0. So because there were like two options here, you have to specify that at f0x you did not find a solution. Romel. I saw this here, because f0x will return 0 in two cases. So what is this? Mu bounded f0x starts at 0 and goes all the way to 0. So this means it's a loop from 0 to 0. So it will return 0. So there's two possibilities. Either, so it checks this equation. This is what it checks. So there are two possibilities. It's equal to 0, or not equal to 0. If it's equal to 0, it will return 0 as the step it found the equation to be true. If it's not equal to 0, it will return 0 because it didn't find the equation. So in both cases here, it will return 0. This is why I'm denoting it this way. However, 1, 0 means that it found the solution of the equation. The other 0 means that it didn't find the solution, but in both cases, you cannot tell it apart. But in any case, this is always 0. And the same thing here, this specification means that in 0 step, you got non-zero solution, meaning that you didn't find it on the 0 step. And then you didn't find it before, and you find it at the place n plus 1, then you return n plus 1. And in all the other cases, you return 0. And you see that this is primitive recursive because by like induction assumption, this will be a previous guy, this will be a primitive recursive thing, primitive recursive, n plus 1, primitive recursive. And these conditions here, we know that these are something is not equal to something is primitive recursive. You still need to do some kind of analysis. And then you know that if this is a predicate, this is a predicate, this is a predicate, that something is, it's a yes-no question basically, or true-false question, then ending true-false questions is still stay in the same realm. And you find that this is primitive recursive. So The idea here is that if you have a bounded mu operator, you do not leave the realm of primitive recursive functions. You were able to do this with only primitive recursive things, meaning constants, projections, successor, substitution, and primitive recursion. So, okay, so what next? So by the way, this allows you to construct many more functions. For example, this function here, you can see. So x divided by y rounded down. So this is also a function, right? That takes two variables, let's say 7 and 5, and you divide 7 by 5, round it down, you get 1, right? So this function is actually a minimum of those natural numbers so that they are less or equal to x, and so m is less or equal to x, and m plus 1 times y already jumps over x. So you can define this as a minimization. And you know that this is a bounded minimization somehow, and you know that, so think about why this bounded. Why does this m, you do not have to check for all m, you only have to check up to some point. And so this here is a bounded minimization, so this function is easily seen to be primitive recursive because bounded minimization is. Also this function, y divides x, right? So if you so this function meaning it's 1 if it divides and 0 otherwise. So you check first of all that remainder x and y is what? It's when you divide the x by y, and what is the remainder? It's you have to subtract from x y times this function. Here you divide x by y, round it down, multiply by y, and subtract from x. You will get the remainder, and then this divides 1 or 0 function is the opposite sign of the remainder. You can think of it this way, yes. Bounded minimization is like a for loop that has that ends. But somehow we just showed that if you have a for loop that ends, so you check the cases and it ends, then it was primitive recursive to begin with. But it also simplifies to the proofs for the functions like this. This was all for the example. Okay, the next slide is we're gonna skip this. So what this is? I'm gonna just say what this is doing. So we proved that there is a bijection between natural numbers and pairs of natural numbers, right? We also proved that there is a bijection between natural numbers and triples of natural numbers. So they're one-to-one correspondence. But what we prove here now is that bijection is primitive recursive. So you can find a function that maps k tuples to just one tuple, and that bijection is primitive recursive, meaning you can write it down as a minimization of something. And that means that, okay, I might tell you there is a bijection between natural numbers and, let's say, triples of natural numbers, but that bijection might not be computable or might not be primitive recursive. But here we prove that the primitive recursive bijections also exist between nk and n. Right? And this is the proof. You can look at it if you want to, but now we want to move to the most important definition of the section. It's a mu operator and mu recursive functions. This is called unbounded mu operator. So now we approach as I said, the main definition. So this is the unbounded mu operator. Pay close attention. This also going into midterm, and it will also go into an exam because we will discuss this very extensively. So I have a function now. So this function takes r plus 1 variables, let's say, and returns 1 variable. And now I'm applying in operators. So again, what is an operator? It takes in, operator is a name for something that takes in a function and produces a different function. So mu f is a new function which has one less variable. So one variable disappeared. So if this had 7 variables, this will have 6 variables. So it's a different function. So what is it? How do I define it on x? It's the smallest solution m of fmx. if it exists, and it's undefined if it's not, it does not exist. So first of all, this operator takes me from defined functions were defined everywhere. This might not be defined. So the only difference between an unbounded operator and a bounded mu operator is that there is no bound. So this can be implemented this way. So you initialize with m equals 0. So while fmx is non-zero, you increase m and you return m. This is it. It's an unbounded while loop. თუ არა აქ ამონახდი სამუდამო. So mu fx returns the smallest solution of the equation fmx, but in case of the bounded operator, you would only go up to n and then stop. If you did not find up to n, you return 0. Now this goes on forever. So if it never finds the solution, it's just omega. If you think of a computer, you just start the program, but it never ends. But you have no way of knowing that it will ever end or not. That is the crucial point. Omegas ვერ მიანიჭებ, იმიტომ რომ ეგ არის მთელი მუღამი. This is the whole point of omega. You cannot assign omega. Omega is not a number. It's just undefined there. If you think of computers, that means your computer is looping somehow, and you have no way of knowing that whether this is looping or not in some cases. სადამდე? ხო და როგორ ეგ არის რომ ვერ მიხვალ, ხო? შენ გინდა რომ გამოგიტანოს კომპიუტერმა რომ undefined ვარო? No, this will not happen. This is the whole point. I'm adding an operation when your computation you cannot recognize somehow that it's undefined. But it's undefined because when you start your while loop, if it never finds a solution, it just goes on forever and you just have no way of knowing when to stop it somehow. So yeah, let's try to do this. So we do not prove that this is not primitive recursive. I encourage you to try to prove that this is primitive. Of course, it's not. For example, you can define Ackermann's function using this. Okay, so yeah, that's actually a good observation. The first thing I did, all my primitive recursive functions were total. Meaning total means that they were defined everywhere. If I do this, I will get functions that are not defined everywhere. For example, let's do this. So let's do one example. Let's take any function. I hope this also is. So let's say fx, so let's call it x1, x2. I don't know, 2x1 plus 5. X2 sadar. So let's subtract x2 and add 3. So subtract it this way. So this is what would be mu f. So mu f is of one variable, right? So it will be a function of one variable because this thing is of two variables. And what this will look at, it will take f and plug in, first it will plug in 0 and x2. And it will look, what is this? So this is 0 plus 3, right? So let's say I want to find, let's give it a concrete case. So let's say I want to compute mu f at 0. Right? So look at unbounded. Bounded has little b underneath. So unbounded mu has no b here. So let's say I'm doing the unbounded mu is I'm looking at fmx. So if I want to find it at x, and I'm checking if fmx is 0 and finding the smallest fmx that this happens. So first I plug in 0 for 0 here. So if I plug in 0, 0, it's 0 plus 3 and it's 3. So it's not 0. Now I'm plugging in f. So let's check the next one. So this would be what? 2 minus 0 plus 3, which is 5, right? So if I plug in 1 and 0 here, so I get 2 here, 2 minus 0 is 0, is 2, 2 plus 3 is 5. So now let's check F2, 0. So this will be what? 2 times 2 is 4 minus 0, 4 plus 3, it's 7. This will continue, so this will continue doing this, and it will never find 0, do you agree? Because this thing is increasing, this thing stays 0, so it will never find 0. So this is undefined. So this function at 0 is undefined. როგორ? Exactly. The fact that the computer is looping, I mathematically, I don't care what your computer is doing. I call it omega. But it's not a number that something that somebody returns. This is exactly denotes the fact that it's just looping. So if I write my program like this, while blah, 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 if for f I plug in what I had on my page, then it will just loop forever. That means it's not defined at 0. But will there be a number for which this thing is defined? So things that I can put here so that this equation becomes 0 for some x. So, yeah. Yeah, so it's actually a good exercise for you to think about on what numbers is this guy defined, and for some of them will be undefined. But the reason why I gave this example is because of your question, because before I had only the functions that were defined everywhere. Those are called total functions. They were defined for every number. Now I have these weird functions, even when I have the simple function like this, which is defined everywhere. Fx1, x2 was defined everywhere. For every input, you have an output. But mu-f now is a function that is not defined everywhere. So clearly, if I define my primitive recursive functions as total functions defined everywhere, and I introduce mu, clearly I added some new functions that are not total. But this is not the reason. This is what I want to stress very much. That you could have initially considered primitive recursive functions that are not defined everywhere, and it still could have added the mu operator, and it still would have enlarged it. The whole point of the mu operator is not that it's just adding functions that are not defined everywhere. It's really philosophically and principally doing a new thing. And we will see that when we move to Turing machines, and this exact same thing can be interpreted also as a Turing machine, which just loops forever. However, let's define what is a mu-recursive function now. A mu-recursive function is the same exact thing as a primitive recursive function. So 1, 2, 3, 4, 5 is exactly the same. So constants, projections, successor, substitution, primitive recursion, and just one more rule is added. The one more rule says that if you have a function which is created from 1, 2, 3, 4, 5, or whatever this creates, then the unbounded mu operator, mu-f, is also in here. So what I basically did, I took primitive recursive functions and I applied mu to all possible cases, and I enlarged my functions. I also involved undefined functions, blah, blah, blah. But this is not the main point that I involved undefined functions. The real shift happens elsewhere, but so clearly every primitive recursive function is mu-recursive, because those 5 rules are still here. How you can create every primitive recursive just using rules 1, 2, 3, 4, 5. But if in your derivation you're also using rule number 6, then you're creating a mu-recursive function. And now we had a proof before that not every primitive recursive function is computable. The same exact proof fails if you also have mu-recursive functions. And this is actually a very hard and good exercise to try to prove that there exists a computable function that is not mu-recursive now, and see why does the same proof not work. In the slides here, it says that that this is because the functions before were defined everywhere. No, it's not defined everywhere. This is not the. You can also consider the proof also fails if we only consider total mu-recursive functions. Meaning what? So let's say I created mu-recursive functions and I only consider the subset of functions which is defined everywhere. So I ban this guy. This guy is removed. So I only consider mu-recursive functions which are defined everywhere. So the subset of whatever is written here. Even for them, the proof fails. You cannot prove that there exists a total computable function which is not mu-recursive. The same proof will not work. And to actually find out where it not works is a rabbit hole. And it's a very useful rabbit hole to go down to. So, bounded mu so the bounded mu doesn't add anything else. So it stays in 1, 2 through 5. We proved this. But if you add an unbounded mu, you get more functions, and the church thesis says that, okay, now your intuitive notion of what it means to compute something, so your algorithm, your intuitive notion of computability is exactly this. This 7 rules, the 6 rules and the 7 rules just says that nothing else. So this 7 rules is exactly everything that can be computed theoretically. And this is church thesis. Because we do not have the definition of computability, so how would we even prove this? However, we take this as a definition of computability, and the fact that this definition of computability is good, and it coincides with our intuition, is the church thesis. IS-7 რაღაცა. So exercise. Okay, let me stop this and I will